Sorry about that. So again, this is MBF3C, grade 11 workplace math, or grade 11 workplace mathematics. No, sorry, grade 11 college preparation mathematics, and my name is Marvin. So again, we are starting class number 11 today. We are going to finish, uh, hopefully finish lesson or unit 1 today and move on to unit 2 next week. We were looking at last class, looking at the exponent laws, and we did a lot of examples dealing with exponent laws. So what I want to do today is finish up this a little bit, and just to show you why. So for example, why is a to the power 0, 1? Why is b to the power 1, b? And why is c to the power negative n equal to 1 over c to the power n? So we're going to do some examples just to show why those rules are the way they are. Okay, so the first one is I'm going to simplify 3 to the power 7 divided by 3 to the power 5. Now the exponent law says when we divide two powers with the same base, we subtract the exponents. The exponents are 7 and 5. So we end up with 3 to the power 7 minus 5, which is 3 squared. And 3 squared means 3 times 3, which is 9. Now, we can do this problem another way, just using multiplication, because 3 to the power 7 means 3 times 3 times 3 times 3 times 3 times 3 times 3, 7 times, 1, 2, 3, 4, 5, 6, 7 threes. And then the bottom, 3 to the power 5 is 3 times 3 times 3 times 3 times 3, 5 threes. If you multiply the top 3 7 times, take your calculator and go do that 3 times 3 times 3 times 3 times 3 times 3 times 3, you'll get 2,187. If you go 3 times 3 times 3 times 3 times 3, you'll get 243. And if you divide those two numbers, you'll get 9. So as you can see, this one gives us 9, and this one here gives us 9. So we get the same answer. So this we know for sure, because we're just multiplying. We know this is right. We know this is right, which means that this must be right as well. Okay? Why is 3 to the power 0, 1? Kind of doesn't make a lot of sense when you think about it, but let's work it out. So exponent laws, when we have a power and we divide, we subtract the exponents. So 3 to the power 4 minus 4 is 0. And we said that 4 to the power, or anything to the power of 0 is 1. Well, why? Well, 3 to the power 4 is 3 times 3 times 3 times 3, which is 81. 3 times 3 times 3 times 3 is 81. And any number divided by itself is 1. So therefore, 3 to the power of 0 is equal to 1. That's how you can do that for any number. You can go 4 to the power of 5 divided by 4 to the power of 5. As long as the two numbers are the same. So you divide two numbers that are the same, you'll get 1. And use exponent laws, you'll get to the power of 0 each and every time. This one is, what does 3 to the power of 1 mean? Well, 3 to the power of 5 divided by 3 to the power of 4 is 3 to the power 5 minus 4. That's what exponent laws say. 5 minus 4 is 1. And we said that anything to the power of 1 is itself. In this case, 3. But if we work this out, 3 to the power 5 is 243. 3 to the power 4 is 81, because remember, 3 to the power 4 is 3 times 3 times 3 times 3, which is 81. And 3 to the power 5 is 3 times 3 times 3 times 3 times 3, which is 243. And if you do the division, 243 divided by 81, you get 3. So both of these give you 3. So therefore, 3 to the power 1 is equal to 3. And this one, we're going to show that a negative exponent means 1 over the same thing with a positive exponent. When we divide, we are subtracting exponents. Okay, so 3 to the power 5 minus 7, which is -2. And the exponent law says that's equal to 1 over the exact same thing with the positive exponent. And 1 over 3 squared, 3 squared is 3 times 3, which is 9, or 1 over 9. If we look at this one, 3 to the power 5 is 3 times 3 times 3 times 3 times 3. And 3 to the power 7 is 3 times 3 times 3 times 3 times 3 times 3 times 3. Then what we know in mathematics is any number. So 3 divided by 3 is 1. 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 And 1 times 1 times 1 times 1 times 1 is 1. And then what's left on the bottom, we have a 3 times 3. That's what's left over there. And 3 times 3 is 3 squared, which is 1 over 9. So we know that 3 to the power of -2 and 1 over 3 to the power of 2 are the same because they get the same answer. Okay, each time you'll get the same answer. This one is 1 over 9, and that one is 1 over 9. So 3 to the power of -2 is the same as 1 over 3 to the power of 2. So for us, just to clear this up, I'm going to get rid of all of those black marks. So when we save this, they don't show up, and then we don't have a big mess on the screen when it's saved. I just do that so I can illustrate for those that are watching. But when we save it, we don't want that to appear. So let's get rid of all of the black marks, and there we go. So when I save that, all you see now is the red, and I can turn that draw feature off. Okay, so that in a nutshell is pretty much it for that particular lesson. Or sorry, lesson number 4. Again, if there's any questions about any of this, feel free to reach out to me using my email address, marvin.osmond@nnacschools.org, or you can call or text me at 807-738-2031. So lesson number 5, the last lesson in this unit, and if we can get through this unit, this is probably the toughest unit, so it won't take us as long to get through the rest of the units. So this particular one, we're still talking about graphs. So we looked at quadratics, which there's 3 different ones that give us a parabola when we graph. We had the vertex form of the equation, we had the one where you get the y-intercept, and then we had the ones where you factor to get the x-intercepts. So there's 3 different forms of the equation, and we could use each of those to help us draw a parabola. So now we're going to look at it, and this is going to be a curve. So in grade 10, you would have studied a linear relation. So linear means when you graph it, you're going to get a straight line. So when you graph something with y's and x's and you get a straight line, there are no powers involved. 0 powers, none. To get a parabola, the x squared term, or sorry, the x term has to be squared. There's got to be an x squared term in there somewhere, or a square term. We're not using x's and y's, we're using a's and b's. There has to be a square term in order for it to be a parabola. Now, this particular one here is called an exponential equation. Okay, an exponential equation gives us a different graph still. We'll take a look at that in a moment. So an exponential equation is of the form y equals a times b to the power of x. So in this particular one here, the x is in the exponent. Okay, so the x is the exponent. So in a linear relation, there are no exponents. In other words, they're all 1. In a quadratic, there's an x squared term, so the exponent will always be 2. But now here, the exponent is the variable. And that gives us a different graph. In these, a can't be 0, because if a were 0, 0 times anything is 0, and 0, that wouldn't give you a graph, it would just be a straight line. It would be the x-axis, actually. B must be a positive number, but not 1, because 1 to any power is simply 1. And again, you would end up with a straight line in that case. So a can't be 0, b can't be 1, and x can be any variable. It can be a positive or a negative number. And we're just going to look at, in this course, where x is an integer. So we're not going to look at fractions and things of that nature. That's for a different course. So we'll stick with positive and whole numbers for the variable. So by definition, an exponential equation is defined by the equation. That should actually be relation, not an equation. An exponential relation is defined by the equation y equals a to the power x. In other words, there has to be an x in the exponent, where the input variable x, okay, occurs in or as an exponent. So an x, don't forget, we call that an independent variable. That's the variable that we get to choose when we want to do the graph. We pick the values of x, and then we solve for y, and then we plot that point on a graph. The exponential curve depends on the exponential equation, and it depends on the value of x. Again, a has got to be greater than 0 and not equal to 1. Okay? There's some examples that are example 1. I'm not going to go through that example because you can all read. So I'll leave that to you. But if we come down here, you can see that if you graph y equals 2 to the power x, you get this equation right here. And the curve goes up to the right. It's called exponential growth. And you graph y equals 1/2 to the power x, you get an exponential decay. So the graph falls to the right as opposed to going up to the right. So up to the right, down to the right. Okay? Both of these graphs will go through the point 0, 1. So the y-intercept will be 1 in both of these cases. And neither graph crosses the x-axis. So they will never, ever touch the x-axis. So we're going to come down, and I'm going to work through a different one with you. So if I come over, and I'm going to see if I can get my, hopefully this will work. I had it set up before, but we had to shut down. I want to get into here, and I want to, oops, get out of here. What I want to do is I want to lock that into place so I can graph. So here we're going to graph y equals 3 to the power x and y equals 3 to the power, or sorry, 1/3 to the power x. Those are the two graphs. Now, before we do that, we can look at the table of values for each one. So we'll look at the table of values for y equals 3 to the power of x. 3 to the power, now we usually pick a lot of points, and we usually start 0 in the middle, 1, 2, 3, 4 points below that, and then 1, 2, 3, 4 points above it. And the more points you have, and you plot on a piece of graph paper, easier it is to graph. Okay, so that's why we pick as many points as we can. Now, in all of these right here, I'm just going to make these all red. So 3 to the negative 4 means 1 over 3 to the power 4, or 1 over 81. 3 to the power negative 3 means 1 over 3 cubed, or 1 over 27. 3 to the negative 2 is 1 over 3 squared, or 1 over 9. 3 to the power negative 1 is 1 over 3 to the power 1, or 1 over 3. 3 to the power 0, anything to the power 0 is 1. Okay, so this one here, I'm just going to fill this one. That's the midpoint. So I want 1, 2, 3, I want 4 points to the left of it, and I want 4 points to the right of it. Same with this one here, 4 points to the left, 4 points to the right. Then I'm going to pick my x values to be 1, 2, 3, and 4. So 3 to the power 1 is 3. If x is 2, 3 to the power 2 is 9. If x is 3, 3 to the power 3 is 27. And if x is 4, 3 to the power 4 is 81. Now, if you look at 81, look at the first one and the last one, you'll see 1 over 81, 81. Look at the next one, 1 over 27, 27. 1 over 9, 9. 1 over 3, 3, 1. 1/3 to the negative 4. So negative means take the reciprocal, which means flip the fraction over and make it a positive number, positive now. So it's going to be 3 over 1, which is 3 to the power 4, 81. 1/3 to the negative 3 means flip it over, becomes 3 over 1 to the power 3, which is 27. 1/3 to the negative 2 means 3 over 1 to the power positive 2, which is 9. And then remember, any number divided by 1 is itself. 1/3 to the power negative 1 is 3 over 1, which is 3. 3 to the power 1 is 3. 1/3 to the power 0, we don't have to do anything because we know anything to the power 0 will always be 1. 1/3 to the power 1, anything to the power 1 is itself, which is 1/3. 1/3 squared means 1/3 times 1/3. 1 times 1 is 1. 3 times 3 is 9. 1/3 cubed means 1/3 times 1/3 times 1/3. 1 times 1 times 1 is 1. 3 times 3 times 3 is 27. And then 1/3 to the power 4 is 1 over 3 times 1 over 3 times 1 over 3 times 1 over 3. 1 times 1 times 1 times 1 is 1. And 3 times 3 times 3 times 3 is 81. So 1 times itself, doesn't matter how many times you multiply 1 by itself, you'll always get 1. Same thing with 0. 0 times itself, actually 0 times anything will give you 0. Okay, so there's a table of values for each of the exponential equations, y to the power of 3x and y to the power of 1/3 x. So now we have a series of questions. What are the values? So how are the values in the tables related? So the values, so here I go 1 over 81, 1 over 27, 1 over 9, 1 over 3, 1, 3, 9, 27, 81. Now if I start over here, I get 81, 27, 9, 3, 1, 1/3, 1/9, 1/27, and 1 over 31. They're mirror images of one another. This one starts from here and works its way up. This one starts up here and works its way down. So the numbers in the y column are mirrors of one another. So the value in each table are mirror images of one another. Graph using decimals. So now if I come over to here, we're going to graph y equals 3 to the power x. I'll just move it, make this a little bit bigger. Y equals 3 to the power of x. And there you go. Now, it looks like when you look at the graph that the red line touches the x-axis, but it doesn't. It gets really, 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 really super close, but it actually doesn't ever touch. It looks like it, but it doesn't. Okay, so it comes down, or sorry, it starts over here, comes to the right, and then goes up, and it goes through the point, oops, 0, 1. So this is 3 to the power x. So if you start from the left and you work your way to the right, the graph goes upward to the right, and as it goes upward, it goes up very, very quickly. Very quickly. Now let's graph the next one. Y equals, now we have 1/3 in a bracket, so we got to make sure we use a bracket. 1/3, and then to the power, oops, I don't need to bracket down there. Bracket, oops, there, and then shift make that X. Oops, I don't want to do that. Okay, where did we go? Oh no, did I shut it down? Okay, let's do that again. Not cooperating today. Let's try that again. So let's get into here and get into, oops, I'm going to make this bigger. Get into my desmos.com. Let's try that again. Y equals 3 to the power x. X, that gives us that graph. And then y equals 1/3 to the x. Y equals bracket 1/3 bracket shift to the exponent x. Okay. So you'll notice here as well, this one, the blue one, 1/3 to the power x, comes down to the right, and this one goes up to the right. Now, if I were to take that graph and I were to spin it 180 degrees, I'm looking at the back side of it, I get the exact same graph. Okay, so when we say they are mirror images of one another, that's what they are here. They are mirror images of one another. Just like the values in the table of values and the graphs itself, they both go through the point 0, 1. We call that the y-intercept. This one, if the value here is a whole number, it goes up to the right. If it's a fraction, less than 1, it goes down to the right. So these are called exponential relations, or these are exponential equations. So we call this exponential growth when it goes up. When it comes down, we call it exponential decay. Decay means it is getting smaller. Okay, so let's get back over into here. I'll just scoot this over here now, make it a bit bigger. So how are the graphs related? So as we said before, they both go through the point 0. If I point to it, click on it, oops, 0, 1. So they both have the same y-intercept. So they both pass through 0, 1. In other words, they have the same y-intercept, and neither graph will cross the x-axis. So it doesn't matter how much, even though it looks like it, if you look at the table of values, it doesn't matter what the value of x is. You can make it a negative 1,000. You'll get a really, 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 really small number, but it won't be 0. Okay, so you would have to basically go to infinity. And even then, it still wouldn't touch. It'd be really, really close, and you would probably need a magnifying glass the size of the Earth to see it, but it still wouldn't touch. Okay, so keep that in mind. So it never touches the x-axis as it is right there, and they have the same y-intercept. 3 to the power x goes up to the right, called exponential growth, and y equals 1/3 to the x goes down to the right. We call that exponential decay. So those are just the terms that we use to describe the graph. So I'm just going to underline this so that it stands out, and this would be exponential decay. Underline that as well. So what I like about Desmos is you can do things to it. And so if I wanted to change a number, for example, if I add a number in front of here, in front of the 1/3 to the power x, let's say I make that a 5. Look what happens. It redraws the graph for us, and look where it crosses the y-axis at the point 5. If I change that to a 9, now it crosses the y-axis at 0, 9. So here, this point right here, that number that's in front of the other part of it gives us the y-intercept. We're not that interested in that right now, but that is indeed what it does do for us. Okay, so now we have one last question I want to take a look at. So which equations represent exponential relation or represent an exponential relation? Y equals 3x minus 7. Now remember, in order for it to be an exponential relation, it has to be of the form y equals a times b to the power x. So in other words, the x has to be in the exponent. Here, x is just a variable. So there are no exponents in this one. So it is not a linear or an exponential relation because the equation is not in the form y equals a times b to the power x. That is, the independent variable x is not an exponent. So doesn't look like this. Actually, in this case, the equation is in the form y equals mx plus b, which means it represents a linear relation. In other words, the graph is a straight line. So this particular one here, if you were to graph that, y equals 3x minus 7, and we'll do that right now. So let's get rid of these, because we're doing a new problem here. Y equals 3x minus 7. So because there are no powers, and remember, no powers, the exponent on the y is 1 and the exponent on the x is 1, but we don't write them. Okay, just understood to be there. So now we have y equals 3x minus 7. This is something you would have studied last year in grade 10, or whenever you did grade 10 mathematics. So we end up with a graph of going up to the right, and this number at the end right here, minus 7, is the y-intercept. So in a lot of these equations, whether we're looking at linear, quadratics, or exponential relations, we can usually pick out the y-intercept by just looking at the equation in most cases. Not all the time, but in a lot you can't. Sometimes you're going to have to do a little bit of work. So to find the y-intercept, all you have to do is substitute the value 0 for x. So if x is 0, 3 times 0 is 0. 0 minus 7 is 7. So that's where we get 0 comma minus 7 from. Okay, so that's how we determine the y-intercept. And that's the same no matter what sort of equation we look at, whether it's linear, quadratic, or exponential. The x value has to be 0, and then we can determine the y-intercept by substituting x equals 0 into whichever equation we have, and we'll always find the y-intercept. The next equation, let's see if I can't move this over any further. It says y equals 4 times 2 to the power of x. Now we know this is going to represent an exponential relation because the equation is in the form y equals a times b to the power x. That is, the independent variable x is an exponent. So let's graph this y equals 4 times 2 to the power of x. So here, y equals 4 bracket. And remember, in mathematics, when it's a bracket, it means we are multiplying. So if we just have y equals 4 times 2, we get a straight line. Then we have to make that an exponent, shift, and the exponent is going to be x. So now this is exponential growth. And as I said, that 4 right here gives us the y-intercept. So if x is 0, anything to the power of 0 is 1. So 2 to the power of 1 is 2 to the power of 0 is 1, and 1 times 4 is 4. There we go. So if x is 0, y is going to be 4. So linear, studied last year. This is what we just did this lesson. And the next one is what happens if we have y equals x squared plus 5x minus 3? Now, it's not of the form y equals a times b to the power x, so there is no x exponent here. So it's not an exponential relation because it's not of this form, y equals a times b to the x. But it's of the form y equals a times x squared plus bx plus c, which means it represents a quadratic relation, or the graph is going to be a parabola. So let's do that. Y equals x squared plus 5x minus 3. And let's graph that. Y equals x. Remember, y equals x squared is the most basic parabola. Vertex is there. Plus 5x. And then minus 3. There we go. So now this represents this equation here, which is a quadratic, which means the graph is a parabola. The purple one here, whoops, the purple graph, what happened to it? The purple graph is right here. That represents a exponential relation. And this one here, 3x minus 7, gives us a straight line. Again, that's what you would have studied last year. So these are the different types of graphs you're now familiar with. And again, Desmos, DESMOS.com is a great website that you can use. So if you want to draw a graph, use it. It's a really good program. And as I said, as you're graphing, as you're typing things in, it does it as you're typing the values in. So for example, if I subtract the minus 7, I just go 3x. There's the new graph now. So minus 7, boom, there we go. So it does it as you're doing it. So it's a really, really useful tool to use when you are graphing equations. Okay, so we have about, I don't know, about 15 minutes left. I don't really want to start the next lesson today because we're not going to get very far. So we're going to take a look at, so one of the things I want to point out was at the end of each unit, you'll see the support question answer. So if you go through each of the lessons, you'll see the answers are here for you. So what you should be doing is looking at or going through each of the lessons and doing the support questions. And then once you've done that, compare your answers to the answers in the back. Don't look back here yet. So don't look at the answers until you've actually completed your solution first. Then you can use this to check, okay? If you just go right to the part and say, oh, that's the answer, and you don't do the work, then you're not actually going to learn anything. So again, this is just here to help you with the support questions. Okay. So if I scroll down here, we get to lesson number 5. So there's an example. There's an example in the lesson material that you would have received. I added another lesson or another graph today. And again, it's in blue and red. And then when you do the key questions, you will have seen 2 examples, and the only difference is the number at the base is changed and everything else remains the same. So you're going to should be able to follow the examples as they're written, and you should be good to go. Okay, so let's scroll back up here again. So if we take a look, I can't go into key questions with you because that would make life too easy for you then. Don't want to make it too easy for you, but not too difficult either. So support questions, again, if we have y equals x squared, that's going to be a quadratic. So it's not going to be exponential. here again, the t is the exponent, so we do for sure have an exponential equation. And then y equals 1.05 to the power of x. And again, the value right here can be anything as long as the x is in the exponent. If the x is in the exponent, then we do for sure have an exponential relation or an exponential equation. So it's important that you do the table of values. And I know when you're dealing with fractions and you have negative exponents, it can be a little tricky. So that's why it's important to come back up and follow the examples that was in the package that you would have received. And there are examples that I did on air with you. So again, exponential growth goes up to the right, exponential decay goes down to the right. That point where it crosses the y-axis is the y-intercept, usually 0, 1, unless the b value, or sorry, this a value up here. So we just a number to the power of x, always, 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 the x-intercept will be 1. But if there's a number in front, like the one that we looked at, 4 times 2 to the power of x, then in that case the y-intercept will be 4. And again, to determine the y-intercept, you let x be 0, and then you solve for y. And that will give you the y-intercept each and every time. So I don't want to go any further today, so we'll stop here for today, and we'll pick up with the next unit on Monday. Thanks for calling, and I'll talk to you on Monday. Bye for now.